This is video 13 in the thermodynamic lectures with Lars Erik. This is about enthalpy, entropy, and Gibbs free energy in ideal gas mixtures. I start with the simplest, which is the ideal gas enthalpy, which is simply the sum of the ideal gas of each pure component times the mole fraction in the gas. That is, that there is no energy change or enthalpy change when we are mixing ideal gases. But when it comes to S and B, it is not that simple. The ideal gas entropy is actually not the sum of the mole fractions and the pure component at constant temperature. The change in ideal gas enthalpy is minus R d ln P. This is from equations 624. That is that is from thermodynamics for pure components. Then the ideal gas entropy minus the ideal gas entropy for the pure component pressure is minus R ln P over the pure component pressure, which is and Pi over P is the mole fraction, and then the ideal gas entropy is the sum of the mole fraction times the ideal gas entropy minus the gas constant times the sum of the mole fractions times ln to the mole fractions for all components. And the ideal gas Gibbs free energy can then be expressed by the mole fraction times the ideal gas free energy plus RT times the sum of the mole fraction times the logarithm of the mole fraction for all components. And then we can say that these are results from this, but perhaps one equation that is easier to remember is the Gibbs free energy of mixing, or for separation. Separation is the opposite process of mixing. And then we have the ideal gas Gibbs free energy of mixing, which is RT times the sum of y I times ln y I. So this is one standard equation which makes it possible to calculate the ideal gas free energy when we mix ideal components. Then I had one example where I ask what is minimum energy for separation of 3.5% CO2 from air at 1 atmosphere and 27 centigrade. So this is what is the theoretical minimum energy needed to separate CO2 from air, which is a sort of CO2 capture. The G mix is then RT times the change, the sum of the y times ln yi for all components, and then I just put in numbers. (1.31 joule per mole Kelvin), that is the gas constant. I selected 27 centigrade because that is 300 Kelvin. And then the mole fraction of CO2 is 0.025. And the mole fraction of the air that is not CO2 is 0.965. And that is 378 joule per mole. That is not easy to relate to anything, but in a way that is an answer to the question. But if we ask per kilo instead for per mole, then we get a number that is perhaps possible to have a relation to. 1 kilo CO2 is 1000 gram, and we divide with the molecular weight of CO2. So that is 22.7 mole. The total CO2 plus air is 22.7 divided by 0.035 is 649 mole. Then the free energy separation, or G mix, is 378 joule per mole times 649 mole, and that is 0.25 megajoule per kilo CO2. So minimum free energy to separate 1 kilo CO2 from air is 0.25 megajoule. And for us working with CO2 capture, this is a theoretical goal, and for most processes this value is much higher, but this is how low that it is possible to get. So this is an example of the calculation of G mix for ideal gas. So this is the end of video 13.